Welcome back. It's been an intense week last week, and I'm sure that it's been an intense weekend. I know for certain that some of you had a lot of things to do. Did we lose anybody over the weekend? Not that you know, is everybody back? In shape? Okay, very well. So this week continues from the first. We had more theory. Now you know how to produce the cosmic rays, you know how to produce the charged particles, the gamma rays, the neutrinos, or at least you have an idea of where to go and look for understanding the astrophysics. But then capsizing, now this is the way we're going to measure them. That should have come before, understanding how they're produced. So it is a pleasure and an honor to present Professor Johannes Knapp, that is going to tell us about how to measure astroparticles. Johannes got his PhD in Karlsruhe in Germany, where he stayed for a while after his PhD to get his habilitation. Then he moved to University of Chicago. Then after that, Leeds University, and then he went to Zeuthen, Zeuthen, which is close by Berlin. He has worked in a number of experiments, including, but not only, Auger, balloon, and the Cherenkov telescope array, CTA, in alphabetical order. And well, I leave the word and the stage to Johannes. Thank you very much for coming and for your time.
So, thank you very much. It's a new experience to be not only watched by students, but also by this hideous machine following me wherever I go. So, yes, I'm talking to you about measuring astroparticles, and it was great to be involved in this school here. You know, this T stands for theoretical physics, okay? Also, you may have realized the lecturers from last week, were basically theoretical physicists. And that's why I've introduced here, well, you see the program again, Blasi, Serpico, and so forth. Also, the titles are rather theoretical. You know, you're introduced to concepts like dark matter, accelerating particle, and so forth. But the question is, how do we know? Yeah? How do we know if, you know, a shock front accelerates particles? And is nature really behaving like that? And I want to give you here a quote first. It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If the theory, doesn't agree with experiment, it's just wrong. Do you know who said that? Yeah? Who? Huh? I don't know. Well, Richard Feynman said that. And he was one of the best physicists in the past century, got a Nobel Prize, but he was also a very good teacher, a very good drummer. He helped develop the atomic bomb. He, you know, obviously helped understanding quantum electrodynamics because he got this prize for it. He translated Mayan hieroglyphs. And also he was the one who found out why the Challenger space shuttle exploded. So he was a really multifaceted individual. And I urge you to look at his lectures and his books that are still, you know, on YouTube and on the web. It's a very interesting personality. But here he is absolutely wrong, absolutely right, that theory on its own, he was a theorist, can't help to explain us the world. It's this interplay between experiments, asking nature a question, yeah? How is it, say for Galileo, how is it that bodies fall in the Earth's gravitational field? Do big bodies fall faster than small bodies and things like that? Only by doing experiments you can test your theory. And what is a theory? A theory is a model of reality. Yeah? So you dream up your model of reality and then you put it to the test. And if the experiment says something different, well then your theory is wrong and you have to modify the model until you describe nature over a broad range of phenomena. So I'm going to give you 5 lectures and loosely characterized. You see, it doesn't really fit very well. It's 6 items here. I give you a quick introduction into astroparticle physics. Maybe Pasquale Blasi has given you a similar thing last week, but a little bit of repetition is perhaps okay. I'll talk then about cosmic rays, which are charged particles, gamma rays. Gamma ray astronomy has been the most productive area of astroparticle physics because much of what we have learned has been learned from gamma ray astronomy, and I explain why. We come to neutrino astronomy, and a really new approach is the multi-messenger approach, where you try to bring these different disciplines together and learn more about the sources of these high energy particles by looking at all 3 aspects. Okay, so here we go. You may have seen this picture here. This is the Knapp Nebula. The star that sits here in the middle was shining as a relatively normal star until the year 2054. Then it exploded in a massive supernova explosion, and that was observed by Chinese astronomers. And they noted down, new star there and there, and they saw it, grow in brightness and then fade back and vanish after a few months. Nowadays, we still see this nebula, which is the gas and dust that has been blown away by this explosion. It's still expanding after more than 1,000 years. Well, 1,000 years about. In the center, we observe a pulsar. So part of that exploding star has formed a neutron star that is spinning very rapidly. It has concentrated the magnetic field that was around that star. So the magnetic field of the pulsar is huge. And the pulsar, think of it like, something like a 2 solar mass object, is spinning 33 times per second around its own axis and is pulling this magnetic field with it. And this produces a strong star wind and accelerates particles, which then hit the surrounding gas and make this gas shine up. So this is what we see here. Okay, I'll try this. This is what we see. The pulsar in the middle produces this wind. The wind hits the gas, and it's shining up in this nice color. So this is a cosmic particle accelerator. And we need such objects to produce energies that we are observing in astroparticle physics. So astroparticles are energetic elementary particles. They rain down on us from outer space, and they cover a huge energy range. We talk about, fast particles starting from about MeV or so onwards. This is the definition, more or less, of gamma rays. Below, it's X-rays and so forth, but MeV is gamma rays. But we observe them up to 10 to the 14 mega electron volts. Yeah? So it's really a very, very high energy. This is macroscopic. This is about the energy of a well-hit tennis ball by a pro on serve. Yeah? But it's concentrated on a proton or on a helium nucleus. Yeah? And as we sit here, we are bombarded about 100 particles per second go through your body. We don't feel anything of it. But these particles, of course, produce ionization in our bodies. They have the potential to change the DNA in one cell or another and make mutations. And so we believe that these cosmic rays are a driver of evolution. Without such cosmic radiation, evolution and mutations would happen much more rarely, so evolution would go slower. Yeah? Now, we do know more or less that the lower energy particles come from our sun. Our sun is very close, so we get a lot of the sun's particles. If we move the sun at the other end of the galaxy, the influence on us would be very, very small, obviously. So just by its proximity, it can dominate the low energy end. But then at higher energies, it's not the sun, it's the sum of the sources of our Milky Way that makes particles. And I'm talking here, say, from 10 GeV to maybe 10 to the 14 electron volts or so. And then we know that the higher energy particles can't be galactic. I will show you that in a moment, or next lecture. They must come from distant galaxies. Yeah? So this huge range of energies is provided by objects in the universe. And we don't know. This is 10 to the 8 tera electron volts. So the biggest man-made accelerator, the LHC at CERN, has a beam energy of 8 tera electron volts. Yeah? We are here 10 to the 8, 100 million times more than what the LHC can do. And we don't really know how nature does it, or we do know, we have some hunches, but for the highest energies, we don't really know what the sources are. And now we can do astrophysics with photons and particles at these high energies we observe, at Earth. On the other hand, if we accept that we have these high energy particles, we can see how they are interacting with the Earth atmosphere. And we can learn about particle physics by using high energy particles from astrophysical origin. So you can call it astroparticle physics. You can also call it particle astrophysics, a little bit what your emphasis is. But the key is we have in the universe objects that can produce these high energy particles, and they come somehow to Earth and we can observe them. Okay, now what are they? Well, if they come from distant objects, they must be stable. If they weren't stable, they would decay on their way and we couldn't observe them. So what are the stable particles we know? Well, it's the proton, the electron, but not only the proton, also helium to iron. And we're talking here about bare nuclei. Yeah? It's not a hydrogen atom. It's just a proton. It's not a helium atom. It's the helium stripped by its electrons, and it's just the nucleus. And as far as we know, they are stable. Of course, there are nuclei, for instance, carbon-14. Yeah? They are unstable, and they would decay. But for most elements, there are stable isotopes, and they can travel on forever. Now, when they are stripped by their electrons, these are all positively charged, and the electron is negatively charged. So what happens if they are charged? They feel the magnetic fields in the cosmos. Magnetic fields are everywhere, near planets, near stars, between galaxies. The strength, of course, is different. Yeah? Close to a star, you have a high magnetic field. On Earth, it's somewhat lower. Between the planets, it's dominated by the solar magnetic field. Between the stars, it's interstellar magnetic fields are lower. And intergalactic is even another factor of 1,000 lower, but it's not zero. And if these particles travel in these magnetic fields, they are somehow deflected. Now, the good thing about those is, because they are electrically charged, we can come up with mechanisms how they gain energy. Yeah? Probably we start out with low energy particles, and somehow they have to gain these massive energies I have explained to you before. So we can accelerate them in electric fields, and an electric field is equivalent to a changing magnetic field. So, we have mechanisms. And you have heard in Pasquale Blasi's lectures how we think particle acceleration is happening. Now, the fact they are deflected is kind of a killer almost. Then if we observe particles arriving at Earth, their direction tells us nothing about where they come from. Yeah? Typical cosmic rays travel for millions of years in our galaxies, are scattered forth and back, and then by chance they hit Earth from some random direction. So we cannot do astronomy with them if they are deflected so much. That's the nice thing on this side. These are other stable particles, photons, light, neutrinos. They are neutral. They travel basically in straight lines. If photons wouldn't travel in straight lines, you couldn't see me standing here. Yeah? You see me because light scattered off me is falling into your eyes. And so we can say, aha, this star stands over here, this star stands over there. We see photons coming from here and so forth. So here we can do astronomy. And that is tremendously helpful because we can study individual objects in the sky. We can say, let's just look at the photons that come from that specific star or from that specific galaxy. Whereas here, whatever we observe is a mix of hundreds, thousands, many thousands sources. They all emit their particles. They are mixed in the galaxy. It's like a soup, And then in the end, you taste the soup by measuring a few particles. But you can't attribute individual particles to individual objects. Okay? Now, because they are neutral, they can't be accelerated in electromagnetic fields. So they must be secondary. Yeah? So we take these particles, we give them a lot of energy, and then we let them react. Either they collide with gas or with dust, or they are deflected in a magnetic field, and by that process, by the deflection, they create photons, or they create neutrinos. Yeah? So they are secondaries from those particles. They are maybe produced for photons, they may be produced in the outer shells of the Crab Nebula, where high energy stuff kicks into gas. There, photons can be produced. And once they manage to escape and travel on, they travel in straight lines until we see them. Yeah? So they are good for astronomy, but they are neutral. They are easy to accelerate, but they are difficult to measure and conclude what the source of them was. Now, there's another type of astroparticle physics, dark matter. Fabio will tell about that in his lectures. I exclude that here altogether. So here again, the energy scale. Yeah? This little range here, factor of 2 in the electron volt range, is what we call visible light. Yeah? It's from 400 to 800 nanometer wavelength or so. Below that, we have radio waves. They go down to 10 to the minus 3 milli-electron volts. And further, of course, you can have radio waves that have any wavelength you like. This here is about the cosmic microwave background radiation. Then we go up, ultraviolet. X-rays are typically KeV. Then MEV are gamma rays. MEV is if you have annihilation of a positron and an electron, you get 2 photons of about half an MeV, so in total 1 MeV. That's the definition of gamma rays. But then all that here exists as well. And people have not had enough fantasy to come up with individual names. So this is all called gamma rays and photons, And it's always a factor of 10 to the 3,000 from here to here, to here, to here, to here, to here. Probably you've never heard about EeV energies or ZeV energies equal. And that is the range of astroparticle physics. Now here you see how far the energy ranges for which we have detected these photons unambiguously. Yeah? So there are instruments, and you will see that later in my lectures, that can see 100 TeV photons and identify them as photons and trace back where they are coming from. Yeah? 100 TeV. The charged particles, yeah, they can be detected out to beyond 10 to the 20 electron volts. We do see unambiguously particles of 10 to the 20 electron volts that look very much like protons or helium. I'll talk to that in one of the lectures, but they exist. Yeah? The electrons we can observe as well, but only till about here. That doesn't mean that there are no electrons out here. This doesn't mean that there are no photons out there. If we have a 10 to the 20 electron volt proton, it will interact sooner or later, and it will produce photons, electrons, neutrinos of energies that are maybe, instead of 10 to the 20, 10 to the 19 or so. Yeah? So if we observe that, there are for sure photons up to here and neutrinos up to there, you know. And these dots just mean we haven't built experiments that are sensitive enough to detect them. How far this is going on, we don't know. We know for sure it can go to infinity. Yeah? We can't have a particle that has a 10 to the 42 electron volts. There's no conceivable process that can make that. It could be that at some stage here, you know, the spectrum just stops. Physics runs out of means to do these very high energies. But we don't know yet. But we know for sure that there are neutrinos going at least up to here and photons that go at least up to here. Now, let me say something about neutrinos. This arrow was much shorter until recently. Yeah? We hypothesized that there are neutrinos down there at low energies. Yeah? In the Big Bang, neutrinos have been produced. They should be now cooled down to about 1 degree Kelvin or so, or 2 degree Kelvin. And this is quite low energy, but they could not be measured so far. Yeah? But what could be measured is neutrinos produced in particle beams at the accelerator and neutrinos coming out of the sun. Our sun is a prolific neutrino source. The fusion reactions in the sun produce with every fusion reaction 2 neutrinos. And there was there were several famous experiments to detect these neutrinos, because by detecting the neutrinos, you can prove that the sun is shining via fusion. Einstein, you know, in his prime time, 1905, 1915, did not have a clue where the sun's energy comes from. All the known energy sources like gravitational energy or burning chemically coal or oil or whatever would not last long enough that the sun could shine several billion years. So at that time, one had no idea where the sun's energy came from. But then in the 1920s, nuclear physics proved that there is a mass defect. Yeah? If you do fusion, substantial energy is released. And that could last for billions of years. And then in the 80s and 90s, experiments were done that could measure these neutrinos that had about a half an MeV or so. And then in 1987, there was a supernova explosion in the Magellanic Cloud. And several experiments on Earth that have been built to measure proton decay, yeah, a proton decaying in some substructure. Theoretically, this was predicted, could be, yeah, but experimentally it was ruled out then at some stage. But these experiments saw neutrinos, about 15 neutrinos in 3 different experiments, all within a narrow space of a few minutes, yeah, from this exploding star. So we knew MeV neutrinos, they have been measured, But by this argument, one was expecting to see something as well here. And there came in now a new class of experiments where people instrumented a huge volume of ice at the South Pole. You know, a cubic kilometer of ice in the South Polar Shield, 2.5 kilometers deep, was instrumented to see neutrinos coming through the Earth and interacting in this volume. And indeed, neutrinos could be detected, and we are now here at a few PeV, 10 to the 15 or so. So this is a new technique here that gave us this. The technique with the underground MEV detectors gave us these, and now we're trying to expand to see neutrinos all the way up there. So it's hanging together, and here is again shown how these processes go together. If you have cosmic rays that are energetic somehow, yeah, they can interact, and if they do, they produce pions. Pions come in two bands, plus or minus, and zero. These make photons right away. These decay into muons. Muons decay a little later, and they make neutrinos. So when we have that, we must have these neutrinos. When we have that, we must have these photons. And if we have appreciable energy on electrons, then they can make photons, high-energy photons, by synchrotron radiation in magnetic fields, by inverse Compton effect, and so forth. And so this is what we can observe in gamma-ray astronomy. This is what we can observe in neutrino astronomy. And this is what we can observe in cosmic ray physics. And, you know, for all of that, you need the high energies in the first place. So these hang together, and if we can observe photons and neutrinos and cosmic rays, we may learn something, and we call that multi-messenger astrophysics. Now, recently, even another player entered. You know that gravitational waves have been observed. Black holes and black holes merge together. You don't see much of that. But if neutron stars merge together, then we have observed that there are photons are emitted. Somehow the outer shell of the neutron stars can produce outbursts, and we see photons. So we expect to see perhaps as well neutrinos. And it's also then part of multi-messenger astrophysics. Okay, so it's clear that the highest energy particles we can observe must come from the most violent environments, the physics under extreme conditions at work in these sources. And it's relatively obvious that the highest energy cosmic rays, the highest energy gammas, and highest energy neutrinos do come from the same source via such a connection here. Yeah? It's almost inconceivable to observe a gamma ray source without charged particles that have produced the gamma rays. There's one other way one could produce photons, and people have thought about it, but it's largely ruled out. Meanwhile, say if you have a very massive particle, something exotic, a magnetic monopole or something, you know, we don't know of, not the standard particles. If this could decay, say in quark, antiquark or E plus, E minus, you know, then you might get here photons out. And obviously, if this is very massive and it decays in a way that its mass is converted into energy, you could produce here very energetic particles. That's a so-called top-down mechanism. You have something very heavy sitting there, and it converts its mass into energy. But it's hypothetical. And so far, there's no experimental evidence that any of the high-energy particles we have observed are produced via such a mechanism. Okay, now let's look at this plot here, where we see as a function of energy of photons, for now, at first for photons, the distance in the universe, how far these photons can travel. Yeah? So for low energy particles, we're talking here EV, so visible light is around here. You know, photons can travel from 10 to the 4 megaparsec. This is 10 gigaparsec. This is about the size of the visible universe. They can travel from the end of the universe to us without being absorbed. We can still observe them. Yeah? So here is the galactic center. Yeah? A megaparsec. So the galactic center is about 30 kiloparsecs away, or 20 kiloparsecs away from us. Our nearest other galaxies, yeah, is about 1 megaparsec, a little bit less. The nearest blazar, so 100 megaparsec, this is about the size of our local galaxy cluster to which we belong and a few other galaxies. You know, they are somewhat clustering together. This is about here. And then this is, the size virtually of the visible universe. And out here we have the maximum of star formation in the early universe. Now, if we come to energies of a TeV or so, you see all of a sudden this distance to which we can see that kind of is strictly reduced. You know, it's falling rapidly by several orders of magnitude if we increase the energy a little bit. And then there's here another feature that is reducing it even more, you know, to galactic center. So at 10 to the 15 electron volts, if we had a source that produced that at the center of our own Milky Way, most of it would be absorbed, would not make it out to us. And then it's relaxing here again, and here something else is kicking in. So what we see here are these characteristic shapes. These are kind of resonance mechanisms that absorb these photons. And the mechanism for that one is the high energy photon that is trying to traveling here is interacting with the cosmic microwave background. And in its center of mass, there is enough energy that they can produce an E plus E minus pair. And when that process is possible, when the energy here is sufficient to make that pair, this process is happening. And all of a sudden, this photon is absorbed. Yeah? And like that, you have here TeV photons that do exactly the same thing. But if you have a TeV photon, you know, and not a PeV photon, then you need here higher energy in order to make that. So if we go here, sorry, I should have written that differently. Let's write here low energy, yeah? And then this is PeV, and this is cosmic microwave background. Yeah? High energy plus low energy, together it's enough to make that. Or we go here, TeV plus infrared light. Infrared light is higher by a few orders of magnitude. This is lower by a few orders of magnitude of that, but in the combination, it's again enough to make these pairs, and the absorption happens. So that means that at these high energies, unfortunately, our universe is opaque to photons. We can't learn about distant sources of high energy photons. They don't make it to us. But of course, if we look at the same thing in neutrinos, yeah? By the way, here you see microwaves down here, infrared, X-rays, gamma rays, and so forth. If we look at neutrinos, neutrinos don't interact at all. So we can observe this part of the sources, of the distant sources, with neutrinos. Yeah? There's no absorption whatsoever. And though in that area where we can't learn from photons, neutrinos are the only messengers that help us. And then cosmic rays, of course, are a totally different thing. Okay, now let's look at the spectra we measure at Earth. The spectrum here means, for instance, we plot how many cosmic rays we get. This is a flux, particles per square meter, per second, per steradian, as a function of the energy of the particle. Yeah? And we have here 12 orders of magnitude in energy. It's a logarithmic scale. And here we have 32 orders of magnitude in flux. And you see barely a structure. It's almost a straight line. Yeah? There's no other process in the universe or in nature that produces a power law distribution like that over so many orders of magnitude. Now, this cosmic rays, this gamma rays, it's looking slightly different, but still it extends to high energies. The flux drops dramatically. It's double logarithmic. If you go up by a factor of 10 in energy, the flux drops by a factor of 500 or so. So it's very, very difficult to build an instrument where you can measure high energy particles because they are so rare. And here neutrinos, here you can plot the individual sources a little bit better, but this is basically on theoretical grounds. Really to measure them is only possible here and then maybe there. So we have steeply falling spectra. Whatever you observe in nature gives you such power law distributions. If you were to go out in the street and you were measuring the height of people, yeah? So at the upper end, you see a few people, many people at 1.70 meters tall, fewer 1.80 meters, even fewer 1.90 meters. You get a few that are 2.20 meters, yeah? But then that's about it. Yeah? So the extremer, so to say, the element you're looking at, the rarer it is. And here you see that nicely demonstrated. Now, here I have shown you what that means in the cosmic ray flux. Down here, we are at about 10 GeV or so, or 100 GeV. We have about 1 particle per square meter in second. So if you build a detector that is 1 square meter, you fly it in the orbit, and you let cosmic ray hit it, you get about 1 particle per second hitting this detector. Yeah? So if you fly your balloon for a few days, or you fly it on the satellite for 3 years, you can collect particles. But if you go a few orders of magnitude up in energy, here for instance in this area, about 10 to the 15 electron volts, it's 1 particle per square meter and year. Yeah? So if you were flying your detector for 3 years in space, you would capture 3 particles. You can't do much with 3 particles. You would not get the money and the opportunity to fly such a small detector because everybody would say, well, there's no chance on Earth that you can learn something from it. Yeah? But things are going on. 1 particle per square kilometer in year. And here 1 particle per square kilometer and century. So how the hell were these red points measured? What kind of detector do you have to have in order to measure this one here? And now, of course, if you optimize a detector to measure these guys, you can't measure with the same detector these guys. It's inefficient. And that is one problem in astroparticle physics. Whatever detector you build, it's only good for maybe 2 or 3 orders of magnitude in energy. And then you have to kind of combine detectors in different energy ranges to learn about the full spectrum. So here, this is the simple equation that dictates that. Yeah? the number of events you measure is determined by the flux of the particles. That is kind of given by nature. We can't make anything about that. And the higher the energy is, the smaller it gets. Times the area of our detector, times the time as long as we measure. Yeah? So say this is a square meter for a typical satellite or balloon experiment. The time you can measure is a few years. You know, that's also a lifetime of a PhD student. You can't say, okay, let's do a PhD. You measure first 100 years and then we see. Okay, that doesn't work. So it's really the area, the only thing where we have a handle if we want to have here a substantial number of events for a relatively small flux. The detector size limits the smallest measurable flux we can have. And if we want to go to high energy, we need to have huge detectors. So how do we go about? Well, we take large natural volumes that become part of our detector. And there's one, that is the atmosphere. It's there, it's for free, it's transparent. Particles that fly into the atmosphere and interact there and do there something. If we can register that, this something, yeah, then we make the atmosphere a part of our detector. Or the neutrinos, they fly through the ice at the South Pole. If they interact there and we can measure what is happening, we can instrument the ice and then we have a cubic kilometer or 10 cubic kilometers of detector size. Now, the good thing is that there happens some multiplication. In space, if we want to detect a particle, the particle has to hit physically our detector. In the atmosphere, it doesn't have to. So for instance, here's a primary particle. It interacts on the top of the atmosphere, and what it does, it produces copiously secondary particles. So instead of one particle of 10 to the 20 electron volts, we have in the end 100 billion secondary particles with 100 MeV or so. Yeah? So all these are secondary particles that are produced with the primary energy. So maybe in the first interaction we produce 1,000 secondaries. They are so energetic that they can produce yet another 100 per collision, and in the end we get something like that, and we call that an extensive shower. Now, if it's happening in the atmosphere, we call it an extensive air shower. If this is happening in the ice, then it's a particle shower in ice. And what we now need to do is we just sample this particle cascade. And because there are so many particles in here, we don't need to measure all of them. We can just measure a subset. And this is indicated here. If we put detectors on the ground, you know, over 20 square kilometers, say. I mean, the particles that are produced here are spread over square kilometers. Yeah? And if we have here a few detectors that see the particles coming down, we can reconstruct from the signals here where the particles came from, how many particles at ground we have been seeing that is proportional to the energy of the primary particle. Now, if we want to identify what that particle was, that is a bit more complicated. We will have to identify whether that was a photon shower or a proton shower. Photon and hadron showers can be told apart reasonably well, but to tell apart a helium-induced shower and a proton shower or an iron shower, that is more complicated. But we are using this multiplication process, yeah? And we do not measure this anymore, but we measure these particles. And if we can reconstruct from what we measure here what this particle was, we have an indirect way of determining what this was, what its energy was, and also what its direction was. So if it were to travel in straight lines, we could point it back to the sources. That's the only way we can access these high energies. There's no chance in hell that you can measure with a small detector that you can fly in orbit 10 to the 20 electron volts. Yeah? So we have to swallow this disadvantage that we have to make this indirect measurement because there's no other way to get at particles with 10 to the 20, 10 to the 18 electron volt energy. Okay, now cosmic rays, nuclei, if they interact in the atmosphere, they make such a shower. And every particle interacts in the atmosphere. The atmosphere, vertically seen, is about 10 interaction length thick. So a particle falling vertical on the atmosphere has a probability of e to the minus 10 to go down without doing an interaction. Yeah? So it's a very tiny fraction. If they come inclined, the effective atmosphere is even thicker. So every cosmic ray interacts in the atmosphere and makes such a shower. If the shower hits our detectors, we can see it. So they are easy to detect. Yeah? Gamma rays, every gamma ray makes an air shower. And it's also easy to detect. Yeah? But there's a background. You know? They're about, depending on energy and direction, 100 to 10,000 times more cosmic rays that make those showers. And if you want to identify photons, you have to get rid of these cosmic rays. The cosmic rays come from all directions, roughly at the same rate. Yeah? So they are everywhere. And you have to get rid of those to see the photons that come from the Knapp nebula or from another gamma ray source. And you have to be able to get rid of those in order to see a clear gamma signal. Neutrinos. Well, neutrinos are those that can travel through the Earth without doing anything. So how are they interacting in our relatively small detector? This is difficult, okay? Very few do interact at all. And also with those, we do have a serious background because neutrinos are not only produced by astrophysical sources, they are also produced by cosmic rays that fall in the Earth atmosphere. Because what are they doing in the Earth atmosphere? So many of these reactions are proton plus nitrogen produces a spray of pions. And pions decay and form neutrinos. Yeah? So we do have this background of neutrinos that are produced in the atmosphere. And these neutrinos, this one here produced in the atmosphere, can also travel through the Earth and be detected in our detector. And of course, we are interested in astrophysical neutrinos that come from a source far away, and they travel and hit our detector. Yeah? And this is the cosmic ray background here to the gamma rays. If we want to have gamma rays, we have to tell the cosmic rays apart. Based on this simulation, we'd say, well, that's relatively easy, okay? This is relatively narrow and well-behaved. Here we have substructures, broader, and so forth. But if you have 10,000 of those, and these showers fluctuate, it's a statistical process. They look sometimes like this, sometimes like that. There are always a few that could be misidentified as photons. Yeah? So we do have, for photons and neutrinos, this background coming from cosmic rays that is complicated. Okay, now this was a very quick introduction. And let me see, I just wanted to have here a different display. Okay, so before we now go on, and talk about the experiments for cosmic rays, gamma rays, neutrinos separately, I thought it's interesting to talk about interactions of particle and radiation with matter. This is at the heart of every detection process in physics, really. Yeah? And maybe some of you may have had lectures on that already during your studies. Then take it as a repetition. Yeah? We're talking about charge and neutral particles and how we detect them, and there are very few fundamental processes that over and over play a role, and that's why we go through them now. So the detection of an object always relies on interactions of particles with a detector. In vision, a photon needs to be absorbed in your eye and make there a signal that you can see, there is a light, or there is the door, and so forth. Hearing, similarly, something produces a wave, the wave travels to your ear, there it's absorbed and it makes a signal, and your brain learns to interpret that. A liquid level, for instance, in your car, how do you measure liquid level? There is a capacitance, and when the liquid raises in the tank, the capacitance of the circuit changes, and you convert that into an electrical signal, and the electrical signal is then displayed on your dashboard. It's always somewhat indirect. Yeah? And with particles, this reaction here, this indirect way of detecting it, is always to let them ionize atoms and record the ionization charge. It's always the electromagnetic interaction that is used to do measurements. So, charged particles, we have E plus, E minus, mu plus, mu minus, protons, pions, heliums, and so forth. All the particles zoo could be listed there. Whenever it has charged particles, carrying a charge, it does ionization, Bremsstrahlung, multiple scattering, Cherenkov light emission, transition radiation emission when a charge travels through a medium. For photons, don't carry charge, so they don't have ionization, they don't have multiple scattering, and so forth. We have the photo effect, the Compton effect, and pair production. And for neutrons, they are hadronic particles. They don't have a charge, so they don't do this stuff here, but they can collide with a proton, and they can be ripped apart, and they can produce pions and so forth. And they also can be captured in nuclei. So these are the basic processes, and we will quickly go through them and learn its basics. So a charged particle is characterized by its mass. It is its charge in multiples of the elementary charge, and its velocity. Yeah? And how does a charged particle hit an element, a nucleus, or an atom in a medium? Well, it hits the electrons in the atomic shell. And you can think of it like the atom sitting here, this is the electron, now the charged particle whizzes through. Yeah? And of course it will never hit that directly. It goes by in some distance, and what this electron feels as a function of time is the electrical field of this particle. When this particle is still over there, the electrical field is relatively small. When the particle is close by, the electrical field is relatively strong. And then when the particle goes off, the field goes down again. So this electron feels an electrical field that is variable in time and gives it a kick. And if this kick is strong enough to overcome the binding energy, well, you have released the electron from the atom and you have an ionization charge. And now in a medium, this is happening all the time. If a fast particle goes through a block of plastic, say, then you have hundreds of those interactions on every centimeter. Yeah? And you release typically many, many electrons, ionization in this. And then it depends on your detector material how you record this charge. Yeah? So the electron feels a kick, and the maximum velocity it can get is determined by the velocity of this particle, and the energy transfer onto this one electron is given by that. Yeah? So there are various constants. The mass of the electron plays a role. The charge of this particle plays a role quadratically. Yeah? So that is important. And the velocity squared plays a role here. So the faster the particle is, the smaller the kinetic energy is. Yeah? Now, the total energy loss of this particle when going through a medium is basically the sum of the individual processes, kicking out here an electron and kicking out there an electron. And if we want to quantify that, this is important, we come up with this equation formulated by Bethe-Bloch. The energy loss of a charged particle going through a medium follows this. So it's the z squared. It's a ratio of z over a in the medium. This is largely 1/2 for the heavier elements, but it's only 1 for hydrogen. Yeah? Hydrogen, there, the charge number and the nuclear number is the same, so this is 1. For all other elements, this is about 1/2. Then here is 1 over beta squared. I think you all know the relativistic notion. Beta equals velocity over speed of light. And then the relativistic gamma factor is 1 divided by square root of 1 minus beta squared. So beta changes from 0 when the particle is at rest to 1 when the particle is flying with the speed of light. Okay? Gamma, on the other hand, if beta is 0, gamma is 1. And if the particle gets faster and faster and faster, so this approaches 1, then 1 minus 1 approaches 0, this thing goes towards infinity. Yeah? Okay. Now, this x here is the path length, and typically this is expressed in units of gram by square centimeters. Of course, your detector has a certain volume, and there are a certain number of atoms in it, and you could calculate then how many scattering centers are here. But now if you squeeze the atoms more together, if you make something that is more dense, yeah, the same number of atoms would be here counted as scattering centers, and this and that situation would be equivalent. That's why we don't care so much about density, and this x is counting the number of atoms independent of density. Yeah? So this is kind of how much matter sits on the path of the particle per square centimeter. Now you see here that there is a small dependence on the particle's mass. Yeah? You don't see the capital M here anywhere, but it's going through this T max. Here somehow is the mass hidden. Yeah? Oops. Here is the equation for T max. So here it's the capital M is hidden here, so the mass doesn't really make much difference. I mentioned already that Z over A is mostly 1/2. For hydrogen, it's 1. So that makes a big difference. Here, this is a density somehow that plays a little effect. doesn't matter much. I is the ionization potential of the medium, so the energy you need to pull one electron out. That doesn't matter much. But here we have gamma dependence, beta squared, gamma squared. But look, this here is within a logarithmic function. So this logarithm of all this, and that's why the dependence on that is not very big. Yeah? So what we get here is a logarithmic rise, and the main dependencies are z squared here and 1 over beta squared there. Yeah? And this ionization as a function of particle energy has then a broad minimum at about beta gamma equals 3. Yeah? And I'll show you that. At low energies, below the minimum, it rises like 1 over b squared. If this goes to 0, this gets big. And above the minimum, it goes basically like logarithm of gamma squared, so a slow logarithmic rise. And here is how you see that graphically. So this is beta times gamma. In a sense, this is a measure of the momentum of the particle. Yeah? Logarithmically, 1, 10, 100,000, 10,000. And this red curve gives you the ionization deposit, so MEV, energy lost per gram per square centimeter. Here is the minimum, between about 2 or 3 to 10. There's almost no change over a wide range of energies. Whereas if you go here, it's changing rapidly if you get slower and slower. And that is very important because it helps you to estimate rather quickly how much a charged particle will lose of energy when it goes through a medium like your detector. Yeah? Here you see the same curves for different elements. You see there are slight differences here from lead to carbon to helium gas. But then there's this outlier. This is hydrogen. This comes by this factor Z over A being 1/2 or being 1/2 or being 1. How do we understand this logarithmic rise? Well, if a particle moves relativistically, we do have length contraction. Yeah? So if the electrical field looks like that for a charged particle at rest, if we look at the electrical field of a charged particle moving relativistically, then in the direction of movement, kind of it is squeezed together, and the electrical field would look like this. So you have a higher electrical field here, and a lower electrical field here and there. And that somehow is responsible. This is another way of explaining why, if you go to higher energies, you have this rise of ionization, because effectively, for all the atoms sitting out there and out here, the electric field looks stronger. This curve is relatively universal. If you take dEdx and divide by z squared, you divide that over, then there's not much dependence in that, and more or less it's a universal curve. Now, ionization is a statistical process. You can't really predict when the next ionization will happen, and on 1 centimeter, how much ionizations you will get. So the whole result is statistical fluctuation, and that's why there's some variation to it. So applications then of this are, if you know the kinetic energy and you measure dEdx, then you can determine Z. And once you know Z, you know the charge of the particle, you know what it was. Was it a carbon? Was it a nitrogen? And so forth. You can measure the minimum ionization, and also that is good to determine Z. And if the particle is stopped altogether, it has lost its energy in your detector, so you know what its energy was independently of ionization. So here you see ionization tracks. These have been made in photographic emulsions. What happens here is that these electrons that are kicked out by ionization kind of break up the material, and if you etch it with some special chemicals in the end, you see this blackening. It's a little bit like photographic film. Yeah? So the light on the photographic film makes a reaction and then pieces are blackened. Now here you see hydrogen. Barely you can see that there is a track. Yeah? It's almost as patchy as the surrounding, but if you know what to look for, you recognize this is the ionization track of a particle with charge 1. With charge 2, remember, ionization goes with Z squared. You see already 4 times as much ionization. 3, 4, 5, 6, 7, 8. 8 squared, 64 times more ionization than here. And now here you start seeing that there are little twigs growing out. Yeah? Or here, for instance, or here. Seemingly, they come out of this ionization track here. Yeah? And this is iron. 26 squared is 500 something times more ionization here than there. And these little twigs out are ionization electrons that have gained by chance so high in energy that they can ionize themselves. So it's a very nice illustration, and if you have calibrated once your ionization, you can now look at an unknown track and you can say, aha, this must have a charge of 8 plus or minus 2. Yeah? The EDX for different nuclei, so if you measure the kinetic energy somehow and you measure the loss of energy, you get these characteristic curves. Yeah? This is the ionization minimum, and the absolute ionization rate goes with Z squared, so you can tell different elements in cosmic rays apart and identify them. So now we take one track and look what happens. So the track is going through material and slowly it's losing its energy. Yeah? So we're starting here, 4 centimeters away from where it stopped, where it lost all its energy. So in a sense, this distance from the end point means high energy here, and then lower and lower energy until it stops. So high energy here, you see this ionization track. Now we go closer by. Beyond the minimum, we rise. The ionization rises with 1 over beta squared. It's getting thicker and thicker. In green, we reach the maximum, and then here it's falling again. It's going down to 0, and then here the particle is stopped. So if you know this ionization loss, you can exactly say what energy the particle had depending on its ionization and its track length and all that. So this is the last, fraction of a millimeter where the ionization looks like that. And in total, the track length here for that was 4 centimeters. So the next important process for charged particles is Bremsstrahlung. If you learned German at school, which some of you may have, then you understand that word as braking radiation. So if you have a charge that is accelerated or slowed down, which is also an acceleration, it gives off an electromagnetic wave. This is very much like if you have a sponge filled with water, and I throw it at you and you catch it, the sponge stops, but the water still splashes out. Kind of the electromagnetic wave kind of travels on. And this is happening whenever a charge is accelerated in any way. If it's deflected a little bit, or if it's slowed down, or if it's accelerated, it gives off this Bremsstrahlung. And the total energy loss by Bremsstrahlung is given here. And here, again, there is a z squared. Yeah? But the energy that is given off is proportional to the energy the particle has. So for instance, if we have an electron here and it's kind of scattered away, then the electron loses some energy and this is given off as a photon. Now here we have the mass of the particle, 1 over m squared. Okay? So this makes that this reaction is largely important for electrons. Electrons are light particles. The next particle to be considered might be the muon. The muon is 100 times, 200 times heavier than the electrons. So m squared is 40,000 times larger for the muon. So the energy loss by muons through Bremsstrahlung is already negligible, almost. Yeah? And you see that here, so the mass is different by a factor of 200, so the energy losses is different by a factor of 40,000. Now look here, change of energy is proportional to something times E. It's somehow proportional to the energy. What is the solution of such a curve? Whenever you have a change that is proportional to a quantity itself, you get an exponential function. Yeah? So E equals E0 times an exponential, and this is some kind of a path length in this case, divided by some characteristic constant. Yeah? So Bremsstrahlung reduces the energy of the electron by an exponential curve. And this is a characteristic length. If a particle, an electron, travels through a medium by the distance x0, then the energy has been reduced by 1 over E. And we call that the radiation length. It's the length by which an electron loses all but 1 over E of its initial energy. So you can work that out. You can also parameterize that. Now, this here, the energy loss is proportional to E. Yeah? So at low energies, that doesn't play a role. Bremsstrahlung is a typical process that is important for somewhat higher energies. So for small electron energies, the loss by ionization is the dominant one. But then at some stage, Bremsstrahlung kicks in. Yeah? And remember, the ionization loss had this logarithmic rise. You grow in energy and the energy loss by ionization is only very slowly growing. But the Bremsstrahlungsloss grows linearly. So at some stage that kicks in and is dominant, and we call the critical energy is the point where these two loss rates are the same. And I can show that here. So this is a typical ionization loss. The minimum is somewhere here, you know, slowly growing. If we go up in energy from 2, 10, 20, 100, 200, not much change here. But then at some stage, Bremsstrahlung kicks in, and it goes linearly with energy, and then up here, it's totally dominating. Here are a few parametrizations, how the critical energy goes with the Z. Yeah? The higher the Z, the energy, so the quicker the Bremsstrahlung gets important. And here it's electrons and muons. Note, here this is Z. Yeah? Here we are calculating the critical energy in GeV, 1000 GeV. This is a TeV here. And here we call it in MeV, 100 MeV or so, is a typical critical energy in solids and in gases. for electrons. Here are some values. You can all look that up, but it is important. And you will find that for your application, no matter what you want to detect, there's always an optimal. I've tricked out this camera. I can't see up here. That's good. Let's see. Okay, it had given up. Good. So you can look up what the values are and then see what kind of detector design you need most. But there is one specific thing that is important, I have to say. If you look at the energy that is radiated through Bremsstrahlungs processes, of course the electron can at most radiate the full energy, can give the full energy onto the photon. I can't give more than that. So we will have this 1/E distribution, up to the full electron energy, and then it stops. And this is a relatively flat curve. So the probability that an electron gives all its energy to the photon is not zero. That's why we call this a catastrophic process. It is possible that Bremsstrahlung gives a lot of energy onto the photon. Okay, and if we sum up the total energy loss, Bremsstrahlung, and ionization, we get this term that comes from ionization and this term that comes from Bremsstrahlung. Here's such a table. By the way, I recommend this book, Review of Particle Properties. It's a book like this, 1,500 pages thick. Everything is in there that a young physicist needs to know about particle physics, about statistics, about detectors, and so forth. And you get it for free from CERN. And you can download it as a PDF on your telephone so that it's always with you. And there are small chapters about detectors, say 5 pages about detectors, 5 pages about statistics, and it's reviewed every 2 years. There's a new one. So I encourage you to look at the corresponding chapters. Unfortunately, astroparticle physics is far too short, but the detector part is quite extensive and quite well written. Okay, now another process of charged particles is multiple scattering. Yeah? So the charge that comes flying through a medium feels the electrical fields of the atoms, and it's kind of bent and kicked away and so forth. And in some, it does an erratic path, and after some distance through a medium, it has been deflected by an angle theta. Yeah? And we can look at what this angle is. It's given here on average, it's some value divided by, momentum. Yeah? It's going with z, and we forget about this. So the larger the momentum, the smaller the deflection. Yeah? So if you have a slow particle, it's deflected a lot. If you have a big particle, fast particle, it's deflected very little. And also it depends on the mass. It's like if a bowling ball, big bowling ball, is driven through little pawns of a game, they will be kicked out of the way. Whereas if you take a table tennis ball, the table tennis ball is deflected a lot. You see that here in these equations, and it is important if you want to know, how far your particle is tracking, because this track here is longer than this dashed line. So you need to correct for that if you calculate ionization. Yeah? Effectively, by multiple scattering, the track is somewhat longer, and the ionization doesn't really care. It's losing energy here and here and here and here and here and so forth. Yeah? So it plays into the details once you take it seriously. And here you see different tracks of protons. As they are stopped here. Yeah? You see they have a good ionization. There's not much deflection and then they stop. These are the bowling balls. Yeah? These are electrons. And you see they are coming in here, and then they are getting curly, and the ionization goes up as they are stopped, and then that's it. And also here. So whenever you see a curly track, for instance, there are these cloud chambers for display where you can see radioactive decays in it and so. You can see there the electrons are the ones with the curly tracks. Yeah? This is multiple scattering for a light particle, and this would be for a heavy particle. Or if you look at tracks of the same incident velocity, the proton travels on and on and on, and then it stopped. The mu meson, half, somewhat lighter, stops early. The electron, it's light, so with the same velocity, it doesn't have much energy. Its energy is quickly stopped, and in the end, it's curved around, If you take the same kinetic energy, the proton stops here, the muon goes much further, the electron goes even further, and in the end, you see the heavy multiple scattering. Cherenkov light, this is another, and for gamma ray astronomy and neutrino astronomy, very important process, also for charged particles. If a charge travels through a medium, it can travel with larger than the speed of light in that medium. Because in the medium, typically speed of light is reduced by the index of refraction. But a relativistic particle doesn't care about that. It just plows on. And so if you have a particle that somewhat sits here, it emits its information, hey, here, I carry an electric charge. And that will move in all directions, and kind of on this ring, the particles feel, aha, there's now all of a sudden a charge. A little time later, it sits here. Again, it's emitting its charge and its information about the electric field and so forth. And if this thing moves faster than the speed of light in the medium, then we get here this front where all these black circles are overlaying. And this is very much the same as if you row on a lake in the boat. If you sit at rest in the boat and you just jump up and down, circular waves will travel away from the boat. But if you're rowing, the waves travel with the speed of sound or waves in water. If you're rowing faster than that, you get this typical bow shock, bow wave here that travels in this direction. The same if an airplane flies above speed of sound in air. You get the supersonic boom, where all these waves overlay. And here it is charged particles, it's electrical fields, and this bow wave here is a bluish light. We call that Cherenkov light. By the way, named after a Russian student. He was a PhD student, and he got the task to find out what the hell is this blue light we see if we have a radioactive source in a jar of water. So this poor guy had to sit down in a cellar, wait for half an hour or so until his eyes have accommodated, and then he started to do experiments. And if he had to switch on the light to do something, had to wait again half an hour until his eyes accommodated. And he came up with a series of clever experiments and explained that effect, and he got a Nobel Prize for it. So if you don't get a Nobel Prize as a PhD student, maybe you didn't work hard enough, or you've got the wrong supervisor.
Or when your supervisor gives you a task, do it.
Yes. Yeah. So that's a very nice effect. It depends on the refractive index. This is the relation of speed of light in vacuum and speed of light in the medium for electromagnetic waves. But charged particles can go faster. But these equations tell you right away that the particle has to be above a certain threshold. If it doesn't reach the speed of light in medium, there is no emission. Yeah? So there's a threshold, and also this emission angle depends on the velocity. Yeah? The faster you go, the more pointed this angle gets, and the emission angle is, so to say, this angle with respect to the direction of the particle. So at the threshold, these bow waves go parallel with the particle. And the faster the particle goes, the more sideways they go. And now you can work out what is that angle if the particle goes really with the speed of light in vacuum. No particle can go faster than that. So there is a maximum angle, yeah, that this Cherenkov light can be emitted. And that is different. It depends on the refractive index, and it's easy trigonometrics and refractive index. The number of photons are emitted. This is number of photons per path length and per wavelength band. You see that this goes with 1 over lambda squared. So the smaller lambda is, the larger the number of photons to be emitted. Yeah? Small lambda means high energy. That's why we have this bluish light. Yeah? It's peeking into the ultraviolet. And that's a very characteristic feature. Of course, it doesn't go to infinity, because the smaller the wavelengths, the more different the n is. Yeah? I've written here n as if it was independent of wavelength, but of course it isn't. In the X-ray range, there is no n that is different from 1 in any medium. And again, the number of photons depends on z squared. So that's always a good thing. You can measure the z with it. From the angle, you can measure the velocity of the particles. That's very nice, because also that helps to identify particles. Yeah? So the angle measures beta, the velocity. This measures z squared. And so that is very important for particle identification. Good. This was charged particles. How do charged particles interact in a medium? And I think I should come to stop. I'm going a little bit more quickly here. We have photoelectric effect, the interaction cross-section. Here, what happens is if the photon interacts, it's gone. Yeah? The energy is transferred onto charged particles somehow. The photon is normally gone. So you characterize that by a probability that such an interaction happens. And the photoelectric effect is this. The photon is absorbed. The energy goes onto the electron. And this goes with z to the 5. So the heavier your material, the better it is in absorbing photons. Here it's the energy of the photon to 7.5. So there's a strong rise with z and a decrease with the photon energy. The higher the photon energy, the lower the probability for that is. The second one is Compton effect. Here the photon is absorbed, but then the electron is in a virtual state and it gives off some energy as a photon. And the energy of this photon depends on the scattering angle. And you see that here. And the characteristic shape of that is this. For one angle, the highest energy you get, so to say, the smallest scattering angle, and the largest scattering angle is then for the lowest energy. And the electrons is what is measured. So even in that process, you do not measure the photon. You measure, in the end, the energy of this electron. Yeah? And if you plot that here, you see a characteristic distribution, and then you say, aha, Compton effect is at work. Whereas here, the electron carries all the energy of the photon. That's the photo effect. And it is important for the energy range 0.1 to 1 MeV. I think I had that here somewhere as well. No. Well, anyway, it's for small photon energies. This is important. For medium energies, the Compton effect is important. And then the third one is pair production. Photon goes into a plus, a minus. You need a nucleus with it, otherwise it's not possible. And here you see pair production probability goes with z squared. And that's it. There's no energy in it. What the hell? Yeah? So of course, you have to have enough energy to make the electron and the positron. Yeah? So below that energy, this process is not possible. But once it is possible, the probability for that is independent of energy. Yeah? And interestingly, the mean free path that belongs to this reaction is just, a factor close to 1 times the radiation length. Remember, this was the characteristic length for energy loss due to Bremsstrahlung. And here you can see this pair production. A photon comes in. You see here nothing in the emulsion or in the film, so no charge here. But then all of a sudden, there are 2 tracks coming out. Yeah? Electron, positron, very close together. So you see that a photon here is converted into an A plus, A minus. And that was used, for instance, for a famous telescope where you have here plates and gas caps in the middle. So the photon comes in, it interacts, produces a pair. They make a track here, they make tracks here, and in the end they are stopped. So you measure the energy in the direction of the one electron, the energy in direction of the other electron, and you can reconstruct what a photon was. And if you take now these 2 processes together, Bremsstrahlung, where an electron makes a photon plus an electron, and a high energy photon that makes 2 electrons, you get that they are forming cascades. So the electron emits a photon. The photon makes 2 electrons. The electrons emit photons, and so forth. And with every step, the characteristic length here is a radiation length. It kind of doubles the particles. And you get here a very simple description of such a shower, how the number of particles goes like 2 to the power t, and t is the step length in units of radiation length. Yeah? So that is the initial rise of number of particles until you reach an energy where this multiplication doesn't work so well, and then there is ionization, absorption, and you get this characteristic curve that describes a shower. So an electromagnetic shower is nicely understood by Bremsstrahlung and pair production, subsequently multiplying the particles. So here you see such showers evolving in these lead plates. The interactions happen, and then you see here the tracks. Yeah? And these are the 3 processes for photons again. So photo effect below 0.1 MeV, between 0.1 and 10, Compton effect above 10 MeV pair production. And you see that here it looks slightly different depending on which element you're in. Photo effect here dominant at low energies. Compton effect somewhere in the middle. And then pair production kicking in at the threshold and reaching a constant value for all the energies. And here for a heavy element, you see the Compton range where Compton dominates is rather small, but also here you see the constant pair production contributions at high energy. Okay, I leave that out. You will get the slides, and maybe you have known much of that already, but these are the main reactions that are the basis of every particle detection wherever you go. And it always goes over the charge. Photons that don't carry a charge need this process whereby they kick out an electron, which then can be measured. Yeah? Okay, and I'll stop it here for today. And we have time, I guess, for 1 or 2 questions.
Thank you very much, Johannes. So, quick questions for Johannes. Good.
Hello.
Yeah.
Okay. Is scintillation light result of Bernstrahlung or ionization processes?
It's somewhere in between. So scintillators are typically some plastic materials with a mixture of molecules that are by ionization kind of either ionized or put in an excited state. And then the de-excitation is the scintillation light. So it is somewhere in between. Without ionization, you don't get scintillation. Yeah? But it's characteristic transitions within these molecules. And the key is they are at a specific wavelength and they are very fast. So scintillation light is typically given off within a nanosecond of particles going through. And that's why they are so useful in experiments.
Hi. In the photon-photon pair production, I saw a nucleus. And what's the role that nucleus play?
Yeah, you know, people often speak about pair production in terms of this, a photon, and then you get two photons out. But you can calculate whether that is possible at all, because what holds is energy and momentum conservation. Yeah? So we have here E gamma, and we have P gamma, and here we have the electron mass, P electron, E electron of these two. And in vacuum, you don't get that to match. In vacuum, this cannot happen because, you know, you can't conserve energy and momentum at the same time. But if you have here a nucleus that can take a little bit of momentum, basically no energy, yeah, then this process is possible, and kind of you have here a slight little correction that makes this electron then real. I make that as an example, okay? Try to calculate energy and momentum here in the rest system. Try it here and see whether you can get it to match without a little correction in energy.
I suggest that we keep the other questions for Johannes for the discussion session in the afternoon. Okay, and
sorry, let me just say one more sentence. So, what is the energy? What is the rest mass of a photon? Okay, so how to call that? M0 equals 0. What is the rest mass of this side? Well, if you go in the rest system of any plus or minus, you have here, sorry. This 1 MeV is 2 times as the mass of this plus the mass of that. Yeah? So, you know, in relativistic kinematics, you learn how to calculate with rest masses, go from one system to the other, and that rest mass is conserved and all that with 4 vectors. So you can't make that without having this little add-on. But since it doesn't take any energy, it just takes a little bit of momentum here, overall this process looks very much like as this was not there. But for strictly calculating it, you need this. Okay, I think we have here a question for the discussions.
we keep the other questions for the discussion, and we thank Johannes again. And I will ring. And as usual, I will ring the bell. There is coffee break upstairs.
Thank you very much. This stopped working, no?
Yeah, there was no battery.
No, I think it's common that people put the finger on the top.